Hello, dear students. Let's see one more example on how to decompose a table into second normal form. In this example, there is a table R given which has 5 attributes A, B, C, D, E, and the functional dependencies defined are as follows: A determines B, B determines E, and C determines D. Question asked is decompose this table into second normal form. First of all, you have to check whether this is not in second normal form. Now, when is a table not in second normal form? Yes, if it has any partial dependencies. What do you mean by partial dependencies? Partial dependency means subset of candidate key. Any subset of candidate key determines non-prime attribute. Non-prime attribute. So first of all, you will have to find out who is the candidate key in this table. And what is the simplest way to find out the candidate key? Out of the given FDs, whatever FDs are given, check the right hand side and see which attribute is missing on the right hand side. Now, on the right hand side, the attributes that are present are B. You can see in the first FD, A determines B. So B is there on the right hand side. D is there on the right hand side. C determines D, and E is there on the right hand side. B determines E. So the keys which are missing are A and C. These are not there. A and C are not there on the right hand side of any functional dependency. That this means that candidate key must contain A and C. I repeat, candidate key must contain A and C. I am not saying that A, C together is candidate key directly. We will have to first of all find out AC closure. And AC closure will definitely contain A and C, correct? Then you watch, due to this A which is there in this closure and due to this dependency which I am ticking on the top, A determines B, B comes in the closure. And because B is there in the closure and C is there in the closure, you see this? Due to this, we get B determines E, so B brings in E, and C determines D. Check the dependency given on the top I am ticking, it brings in D. That means if you find AC closure, then it determines all the attributes of the table. So AC is the candidate key. But just check from since the previous videos, I have been warning you that don't come to any conclusion very early. Okay, we know that AC is the candidate key, accepted. But is there any other candidate key? There can be more than one candidate key, and you have to find out all the candidate keys. Remember one thing: A and C must be the part of candidate key. Candidate key cannot be formed without A and C because A and C is missing on the right hand side. So somebody, will rubbishly, I hate this word, but rubbishly find out, is BD candidate key? Now this is just a waste of time. Come on. BD cannot be candidate key because A and C have to be present in the candidate key. Just for fun, find out BD closure. It is a waste of time. This will contain B and D, definitely. Now, due to this B, and due to the FD that I am ticking on the top, B determines E comes in the closure. And now notice D does not determine anything out of the given FDs, and E does not determine anything out of the given FDs. So BD plus is going to contain BDE. That means BD together are not able to recognize or determine all the attributes. The point is that any candidate key, whatever is the candidate key, must contain A and C. So it's out of question to check whether BD is the candidate key or DE is the candidate key. It's a waste of time, isn't it? But then really, AC is the candidate key. Is there any more candidate key? Now check that if AC is the candidate key and AC has to be there in the candidate key, then asking whether ACD is the candidate key is rubbish, because this already contains AC and AC alone can determine all the attributes A, B, C, D, E. Are you understanding? Then this is a super key if you add this D attribute to this candidate key. Or asking whether ACE is the candidate key. No, This is a super key. This is a super key because these already contain the candidate keys, isn't it? So adding anything in AC will create super key, and you can't create a candidate key without A and C. So AC is the only candidate key. I hope you have understood. So AC is the candidate key we have found out because AC closure contains all this. Now watch this. The functional dependency which I am underlining is a partial dependency because left hand side is only A and the candidate key is AC. So left hand side is the part of the candidate key, and watch the right hand side B here is not the part of candidate key. So it is a non-prime attribute. By the way, recall AC is the candidate key, then A and C are called prime attributes. Prime attributes. The attributes which are forming the candidate key are called prime attributes. So in this example, B is a non-prime attribute, D is a non-prime attribute, and E. These three are non-prime attributes. So what do you mean by partial dependency? The left hand side of the dependency is a subset of the candidate key. Okay, A is the subset of AC, and right hand side of the dependency is a non-prime attribute, then such a dependency is known as partial dependency. That's it. You have now found that this table R is not into NF. Not into NF. Because to be into NF, no such partial dependencies must be present. Now watch this. B determines E. Check this thoughtfully. You just check this thoroughly. B determines E. Is the left hand side part of candidate key? Remember, candidate key is AC. Now B is not a part of candidate key. Okay. And what about right hand side? This is a non-prime attribute. Listen very carefully. Hello students. Listen very carefully. This is not a partial dependency. What is partial dependency? Left hand side has to be part of the candidate key and right hand side has to be a non-prime attribute. Okay, in this dependency, E is a non-prime attribute, right hand side is a non-prime attribute, but left hand side is not the part of candidate key. Such dependencies, B determines E, is in fact non-prime attribute is determining a non-prime attribute. Are you understanding? Check what is B in our example, non-prime. What is E? Non-prime. Then non-prime determines a non-prime. This is not a partial dependency. This is called as transitive dependency, and we will see that this is necessary to be removed. Yes, even such dependencies should be removed, but after removing we will get 3NF. So these dependencies B determines E will be seen in third normal form. In second normal form, the condition is there should be no partial dependencies. So just check this. I hope you have understood. A determines B is a partial dependency. B determines E is not a partial dependency, but C determines E is a partial dependency. Left hand side is a part of candidate key. AC is the candidate key and left hand side contains only C. And right hand side is non-prime attribute. D is a non-prime attribute. So there are two partial dependencies. I have made it clear. Note, B determines E is transitive will be seen in third normal form. So we leave that dependency as it is. So how do you remove these partial dependencies? Yes, take the first partial dependencies A determines B and you find A closure, left hand side closure. A closure will definitely contain A, and because A determines B, A closure will contain B. And because B determines E, check this, check the dependencies given above. Check that B determines E. So B will bring in E, correct? And now nothing else will come in. A, B, E will be the closure of A plus. And what was the second partial dependency? Yes, C determines D is the second partial dependency, isn't it? These are the two partial dependencies. So we find C closure. C closure will contain C, definitely. And because C determines D, D will be there in this dependency, correct? And nothing more can be there. Check the dependencies given above in the original table. So what we do next? We will write all the attributes A, B, C, D, E of our table, and we say that A closure is BE. So A closure contains BE, so A will take away B and E with it. So it'll strike away B and E. Okay. So this forms one table. Let us call this as R1. I hope you are understanding very well. And we did for this C determines E. For this partial dependency, we found C closure. So we say C will take away D. So we will write CD and we will strike out D. We can see that C has taken away D with it and A has taken away B and E. So this is the another table. And now whatever we have not striked out, A and C, observe A and C are still remaining, will form the third table. R3 contains AC. These are the three tables created. Now watch out that these two tables R2 and R3 have common attribute C, and R1 and R3 have common attribute A. I hope you are understanding, isn't it? So, and you can also check that these common attributes are candidate keys in one of the tables. But you just can't forget, after decomposing these tables, you just see which dependencies are applicable on each of the tables. Let me scroll up. Here we go. You check out of the three dependencies given, A determines B, A determines B is applicable over here. Okay, because A and B are present in this table. Correct. Then B determines E. Observe the second one I am ticking on top. B determines E is also applicable to R1. Fine, because B and E are there in this. Well, okay. Then what about R2? Which dependency is applicable? You see on top I am ticking C determines D. So C determines D is applicable on R2. Fine. And what about R3? R3 is containing A and C, which was candidate key of the original table. Remember, AC was the candidate key of the original table. That means AC determines AC. There is no dependency as such defined on R3. That's fine. Now, check it out. In R1, think here, rigorously you think here. In R1, who is the candidate key? Just find A plus here, A plus. A plus is going to contain A, B, E. Come on, I am wasting the time now, because this is how the table R1 was formed. We found A plus and A plus has A, B, E. Definitely A has ability to recognize or determine all the attributes of R1. So A is the candidate key of R1. I hope you are understanding. A is the candidate key. Then talk about the partial dependency A determines B. Talk about this. Sorry for this. I'll rewrite this. Talk about A determines B. There is a dependency over here. A determines B. Is this partial dependency? No, because left hand side is candidate key. Yes, A is the candidate key of R1. So it is not the part of the candidate key. This is complete candidate key. And right hand side, yes, it is a non-prime attribute, isn't it? It's a non-prime attribute. B is a non-prime, so this is not partial, because left hand side is perfectly a candidate key. It is not the part of candidate key. What about the other dependency? B determines E, isn't it? This was the dependency. Check R1. R1 has A, B, E. B determines E. Is this partial? No. Here B determines E. Non-prime attribute determines non-prime attribute. So this is for 3NF. Leave it. Okay, who is the candidate key in R2? Come on, C is the candidate key. That's how we got this, isn't it? C plus is CD. That's how we got this. So C has ability to determine all the attributes of R2. Then talk about this dependency. C determines D. Is this partial dependency? No, because left hand side is perfectly a candidate key, complete candidate key. Then this is not partial. What about R3? Come on, AC was the candidate key of the original table, and there are no dependencies as such defined on this. AC determines AC here. That means all the dependencies defined on R1, R2, R3 are not partial. So we say the decomposed tables. Remember, listen very carefully. The decomposed tables R1, R2, R3, all three tables are in second normal form. Thank you very much.